Good afternoon, and I'm Gitanjali R. Soni. I just hope that I am visible also. I hope I'm audible. Am I audible to everyone?
You're audible, but not visible.
I know
Yes.
it's taking a little while, thanks to the internet connection, but I'm so happy that we had such a fruitful, brilliant first session in the first half of the morning. And now we are going to have even more interactive and much more learning experience because this is Seaweed India 2021. And we know that we are learning quite a lot about the possibilities and what are going to be the coming future adventures for us in the seaweed industry. So right now, without any further ado, so am I visible now?
You are.
All right,
Very
thank you.
good.
So good afternoon, namaskar formally, I would say everyone. I'm Gitanjali R. Soni and I'm representing AgriPost today. And this has been such an enriching experience since morning. And as I said, the second session, which is session number 2 technical session, is on improved seaweed farming technologies and practices. And this session will be chaired by Dr. Stephen Kran, CSO, the seaweed company Purple Turtle, Tamil Nadu. And although, we know quite a lot about our chair of the session, but I would like to say something more about him because his main fields of expertise are aquaculture of seaweeds, sustainable development of algal resources, industrial applications of seaweeds and usage of seaweeds in animal feed, aquaculture, biotechnology, and biomedicine. Also, as co-founder of Seaweed Company in 2018, and this company with complete horizontal integral developing the whole seaweed value chain from cultivating to biostimulant feed, food biometrics, and pharma. Furthermore, he's involved in the development of large-scale seaweed biomass cultivation programs for the food and functional ingredients industry and exploring protein extraction for from seaweeds for animal feed industries. So there is quite a lot. Dr. Kran was president of the International Seaweed Association 2016 to 2019 and currently a business coach for increasing the export of Europe of 14 Indonesian seaweed companies under the Dutch Ministry of Foreign Affairs Development Program, CBI. Although, this was not very easy. There is so much to talk about, but today our prime focus is on all the speakers we have and our honorable chairperson who's with us. He's going to introduce the rest of the session. So now over to Dr. Stephen Kran. Please welcome, sir.
Thank you very much for this very, very kind introduction. I don't often think that extensive, so well done. So as already was announced, Professor Reddy has been called away for government meetings and with ministers because originally he was going to chair this session, but the honor is fallen on me to do this now. So Professor Reddy has also a presentation, so I'm going to introduce him now, and then we play the presentation, and the other 4 or 3 people in the session, they are actually present, so they will present live. So Professor Reddy is at the moment Chief Executive Officer of the Indian Center for Climate and Societal Impact Research. And Professor Reddy has run or has been organizing several work groups in quite a few institutions actually. Before joining the center, Dr. Reddy held a position as DBT Energy Bioscience Chair Professor of the DBT ICT Center for Energy Biosciences, the Institute of Chemical Technology in Mumbai for about 2 years. And he also worked before that in the Central Salt Marine Chemical Research Institute in Bangladesh in divisional chair and chief scientist. And of course, his fame precedes Professor Reddy because he has also won several national technology awards and scholarships besides serving important scientific committees in various capacities on editorial boards of the Journal of Applied Ecology. And he holds also a distinguished record with established scientific credentials, authoring 90 publications, 18 book chapters, 3 patents, and 4 books. So let's start with this presentation now, and then we will catch up after the presentation.
Yeah, but Stefan, I will request you just one thing. Let us make it more interactive. We can have more questions and what impact the outcome. So that will be helpful to the government as well as all the stakeholders. We should focus that one also. Okay, after the presentation, we'll have more interactive things.
Yeah, but we do that after the presentation. I take it.
Yes, sir.
That is.
Hello everyone. At the outset, I would like to thank the organizers for allowing me to share my research experiences on seaweed farming and utilization in India. I would also like to thank CSIR for allowing me to experiment with my ideas and contribute to the advancement of seaweed research in India. Seaweed cultivation is now the world's fastest growing aquaculture sector and registered more than 28% share of total global aquaculture production in 2018. Seaweed could play an important role beyond serving as a source of nutrients and food, but also in the fight against some of the worst issues plaguing the world today, such as climate change and ocean pollution. Like agriculture croplands, seaweeds are cultivable but do not need arable land, fresh water, fertilizer. They can be farmed in the sea and non-arable land along the sea coast. Seaweed cultivation is a regenerative and restorative and helps to realize economic, social, and environmental benefits sustainably. Although seaweeds in India are utilized exclusively for the extraction of typical hydrocolloids, agar, and alginate from the wild harvest, the eukaryotic cultivation has heralded commercial farming of seaweeds in the country. Seaweeds have all potentials to strengthen and promote the recently launched Atmanirbhar Bharat Abhigyana Yojana and inclusive blue economy in India. In this presentation, I will briefly dwell on the scope and potentials of seaweed farming for inclusive economic growth of coastal rural areas in the country. Also points to research gap areas and challenges that need to be addressed for achieving the accelerated progress in the seaweed sector. I would like to take this opportunity to introduce my organization, the Indian Center for Climate and Societal Impacts Research, which is a non-profit and public-private partnership organization established in August 2008, registered under Section 25 of the Companies Act 1956 and is located at Mandavi, Kutch, Gujarat, India. The mandate of this organization is to study the climate evolution, impacts of climate change on rural sector, societal adaptation, finding solutions for the reversal of climate change, etc. It also provides a weather forecast bulletin to farmer and the industry. In recent times, the scope of activities expanded and forayed into seaweed field given their climate change mitigation potential and societal, economic and ecological benefits. So the seaweed activity is supported by consortium consisting of Excel, Pedialyte and Mamta group of industries. We are open to national and international collaborations and happy to work with like-minded visionary partners.
Growing world population and climate change are the two global challenges pushing hard the sustainability. India has all the more reasons to focus on ocean resources for meeting the future food and energy security. By 2030, India will be the world's most populous country with more than 1.4 billion people. World population is increasing by 35%, while India's population is increasing by 41%, indicating greater demand for the production of food and energy. Despite oceans cover more than 70% of the Earth's surface, the food production from the ocean resources accounts for mere 1.2% of the global food production each year. There is a need and scope for exploring the ocean resources for future food and energy needs.
In India, Tamil Nadu on the southeast coast and Gujarat on the northwest coast are rich in seaweed resources and account for maximum seaweed biodiversity as compared to other maritime states. However, seaweed collection from wild beds is an intensive activity in Tamil Nadu and more than 2,000 households have adopted seaweed collection as the mainstay of their income, and the annual market value of the harvested crop estimated at USD 4.2 million. In India, seaweeds are utilized exclusively for the production of phycocolloids like agar and alginate from the material harvested from the wild beds. Among the red seaweeds, Gelidiella and Gracilaria are collected and supplied to agar processing industries, while Sargassum and Turbinaria are harvested for alginate processing units. There are total 32 seaweed processing units operating in the country. Most of these industries fall under MSMEs category. The annual production of agar by domestic industries estimated at 260 tons, whereas alginates 330 tons per annum. Some agar producing industries do import agrophytes from Spain, Indonesia, besides local suppliers.
It is very important to have a market watch for both regional and international level to make successful strategies. The seaweed market report by a leading group in India made projections for 5 years from 2018 to 2023. According to their market analysis, the global production is estimated at 35.9 million tons fresh weight with a market value of USD 14 billion for 2018 and projected to reach to 53.7 million tons fresh weight with a market value of $21 billion by 2023. The Asia Pacific market share continued to remain at top with more than 60%, followed by North America and Europe with 19.2% and 10.5% respectively for 2018. The red seaweeds market share with 60% dominate the rest two brown and green seaweeds. The entire global production, that is 32 million tons fresh weight, comes from just 10 countries in the world. Most of these countries predominantly from Asia, accounting for 99% of the total production. China tops the list in the production and accounts for 50% of the global production with 18.5 million tons fresh weight, followed by Indonesia with 9.3 million tons fresh weight, accounting for 28.7% of the total production. We wish to see India in the global seaweed map in the near future. As we said, India provides several opportunities for leveraging seaweed resources for addressing some hard-pressing national needs. Considering the global demand for agrophytes, India can prioritize farming of agrophytes over others. We have a very valuable resource, Gracilaria dura, producing superior grade agar similar to that of produced from Gelidium. There is also growing interest in COVID times to use seaweeds in human diets in India. India also stands top in livestock population, and there exists a scope for using seaweed ingredients in the animal diets to mitigate methane emission in the burps and improve the health of animal. India has an obligation to reduce the emission intensities of its GDP by 33 to 35% over 2005 level by 2030, along with other emission reduction commitments. Seaweed farming not only help to capture the CO2 emissions, but also provide livelihoods to coastal people while supporting the ecosystem health. Similarly, there is a significant scope for making bioplastic using seaweed polysaccharides, substituting the plastic with a significant environmental issues. The biofuels from seaweed sources also contribute to the proposed emission cutting strategies. The exclusive economic zone of India is very vast with more than 2 million square kilometers and also got more than 1.4 million hectares of sandy and marshy wastelands that effectively can be used for farming of economically important seaweeds. Recently, Government of India also announced a policy with a special grant to promote the seaweed sector in India with a target to increase the seaweed production to 1 million tons fresh weight by 2025.
India has many economically important seaweeds like any other Asian country except for the kelps that grow cold waters. There is considerable scope for developing both cultivation and downstream processing technologies for the utilization and value addition of Indian seaweed resources. The seaweed resources that we have in India represent edible, phycocolloid, and industrial importance. There is considerable scope and opportunities for developing innovative farming technologies for commercial scale cultivation of economically important seaweeds. Seaweeds offer huge economic, societal, and environmental benefits, improving life on this planet Earth. Eucalyptides have been introduced and found in numerous countries having tropical climate across the world due to its high adaptability and production potentials coupled with surging global market demands. A few fragments of Kappa ficus have been obtained in 1994 from Japan, observing all protocols of introduction and quarantine. After acclimatization in the laboratory culture, the algae was introduced in the sea in confined conditions, employing in perforated bag method in Gujarat and later in Mandapam, Tamil Nadu. The MAC method of cultivation was discontinued in 2000 after its occurrence has been reported from Indian waters. The first experimental cultivation of Kappa ficus in coastal waters of Mandapam began in September 1995 using the perforated transparent polythene bag method. In 1998, open culture method of namely fixed bottom monoline was adopted to overcome shortfalls of the bag method. This method was replaced with the net bag method in 2000 to minimize the grazing and loss of cultivated biomass. In 2003, the raft method of cultivation was adopted to simplify the overall cultivation operations. Currently, the raft method is widely practiced by all Kappa ficus growers in the country. To further strengthen the Kappa ficus cultivation in India, we have for the first time developed tissue culture techniques for large-scale production of micropropagules. We have successfully developed an innovative process for the mass production of tiny micropropagules from pigmented filamentous callus. The findings of this landmark research have far-reaching implications in developing land-based nursery for seedling production, as well as the pigmented filamentous callus permits for undertaking genetic manipulation studies aimed at generating genetically improved strains, enhancing the sustainability of eukaryote farming. Also, the callus can be used for the long-term preservation of germplasm. The field cultivation of tissue culture progeny was initiated to study and compare the growth performance over farmed plants. The plants generated from tissue culture showed an increased growth rate of 1.5 times higher than controls in the field cultivation. Also, the carrageenan yield of tissue culture progeny remained unaffected and comparable in terms of quality and quantity. Farming of such improved varieties helps the farmer to realize enhanced value for his crop and efforts. This slide provides data on yearly production, value, and number of beneficiaries engaged in the eukaryote farming in India from 2005 to 2016. There has been an exponential growth in seaweed production, market value, and the number of people joining the cultivation, but the year 2014 encountered a serious setback, recording the lowest production ever since its inception, and the lag continues even in 2021, although a marginal increase showing. The crashing of the farm was attributed to unprecedented high temperatures. The entire crop showed signs of sudden whitening. The algae experts, both in the Philippines and Indonesia, could not help in establishing the cause for this decay. However, it was learned that similar situations have been experienced even on the international landscape. Recovery is made possible by quickly shifting material from unaffected sites. Farmers are since then working to multiply the small quantity of planting material brought from Gujarat under the guidance of industry, and now all the farmers have fresh startup material to resume the cultivation activity.
Here is an opportunity available for India to capitalize from the void created by short supply of geladium for agar in the world market. It is evident from the past efforts that it is hard to cultivate geladium in the sea. Therefore, geladium was harvested from wild beds and supplied to global agar industries for agar production. Morocco is the major supplier of geladium with more than 50% of share of the global agar industry. So the restrictions imposed on wild collection by Morocco resulted into shortage of agar in the world market. In this context, India found out an alternative resource, Gracilaria dura, providing superior grade agar similar to that of produced from Geladium. India can capitalize this opportunity and emerge as an international player in the global agar market. The slide shown here contains profuse growth of Gracilaria dura in the sea. The upper one shows Gracilaria dura in tubular net method, whereas the bottom one is a monoline method. It is also propagated through vegetatively like carrageenophytes. The pilot studies conducted in the sea has given very promising results for further scaling up to commercial activity. This algae can be formed at least for 8 months in a year, except for monsoon periods in India. To enhance the efficiency of utilization of feedstock and sustainability of downstream process technology, we went ahead in developing innovative downstream technologies in biorefinery model. The downstream technology depicted in this slide shows an integrated approach to recover as many as 5 products such as pigment, lipid, agar, cellulose, and sap from fresh seaweed feedstock. The advantage of this process is manifold, ranging from densification of product, low usage of input chemicals, improved quality of agar, and maximization of feedstock usage. Also, some reagents used in this process were recycled without compromising on the quality and yield of product to increase the cost effectivity of entire process. Each component recovered from this process can be used for further value addition studies. The versatility of biorefinery process developed for red seaweeds was further evaluated suitability for green seaweeds as well. We could succeed in recovering all major components of primary feedstock such as sap, lipids, albumin, protein, cellulose. The amino acid profile of protein, fatty acid profile of lipids, and albumin FTR chromatogram well compared with those products recovered individually from primary biomass. Also, the studies on digestibility of protein showed very encouraging results, indicating its suitability for supplementing in human foods. The success achieved in developing biorefinery process for red and green seaweed has further inspired to develop similar process for brown seaweeds as well. As sargassum being an abundant and most commonly growing resource on Indian coast, we have chosen to develop a biorefinery model for that eventually led to develop a zero effluent process. The schematic process shown in this slide clearly demonstrate recovery of sap, alginic acid, protein, and cellulose from fresh feedstock. The effluent obtained through this process was neutralized and evaporated to dry solid powder. So we are exploring the end use of salt. Here is yet another important innovation developed to demonstrate a simple method for production of germlings routinely from vulva. In this process, we have employed protoplasts as propagules against spores using cell wall digesting enzymes such as cellulase. The protoplasts produced were seeded on both sides of a polyacrylic sheet in a seeding tank with clean seawater first, and then shifted them to propagating tank with enriched seawater medium to further boost their growth under controlled conditions. This helped to achieve the production of large number of propagules of uniform quality. In order to increase the cost effectivity of the production of propagules from the protoplast route, so the enzyme used for protoplast production was recycled for 5 times successfully without compromising on the yield and viability of protoplast. This process is of great help in developing nursery models for seaweeds. Now, open sea cultivation comes with innumerable challenges and limitations. Seaweed cultivation in India is seasonal and interrupted by monsoon. Seaweed cultivation also vulnerable to grazing, diseases, epiphytes, and sometimes the crop as well as cultivation infrastructure is lost due to cyclones. The seasonality causes significant variations in crop yields, quality and yield of product, making the crop unsuitable for niche market or high-end applications. It is desired to have innovative cultivation technologies for land-based farming of seaweeds to achieve greater consistency in yield and quality of the crop, besides enabling seaweed farming round the year. To be competent in global level, India need to have a strong S&T program addressing some of the challenges in both upstream and downstream areas. Indian scientists need to develop robust cultivation technologies and climate resilient cultivars. We also need to raise ourselves in developing solutions addressing national needs such as bioplastics and climate mitigation. The existing infrastructure need to be modernized in the light of current needs and future demands. Since seaweed industry is in its formative stage, it requires a special attention, support, and promotion in a way of providing assistance and regulatory clearances in timely manner to stakeholders. Unfortunately, no university in India teaches seaweeds at present. It is very disturbing when India is looking to emerge as a global player in the seaweed sector. I would also take this opportunity to pitch for a dedicated center, National Center for Seaweed Research, created to accelerate the advanced programs supporting the seaweed industry in the country.
I would like to take this opportunity to thank my promoters, Excel Industries, Pidilite, Mamta Group, for generously supporting the seaweed project and also permitting me to participate in this workshop. Thank you so much.
Okay, that was a wonderful presentation from Professor Reddy, and we have a few minutes for questions and interaction indeed. And just to kick it off, I have a question to the forum and the people joining this meeting here. There is if you look at the whole seaweed sector in India, there is a kind of a push for Ficus. And as I'm myself involved in this industry in Indonesia, and I know how hard it is for them already to compete with the Chinese, what is the chance for India to succeed in a viable Ficus production for carrageenan? Secondly, you also, or Professor Reddy also showed in his presentation that the Gracilaria dura is a wonderful or good alternative for Gelidium sesquipedale from Morocco. And Morocco has about half the world market, and they stop now with wild harvest. So there is a very clear opportunity that can be achieved through aquaculture. So looking at these things, I would almost be inclined to say for India to say, well, focus on the Gracilaria dura, because that is an area you can play in and actually become viable and well, profitable. So any comments on that?
Dr. Johnson? Yeah, Dr. Biorefinery, hello.
Go ahead, Ravi.
I think.
Yeah, I think I will be giving my presentation, and there this Gracilaria will be covered. So I'll reserve my comments after my presentation.
Okay, no, very good. That's fine. That's fine. So I don't know if somebody else wants to comment on this.
Yeah, I think that Dr. Johnson could do.
But please go ahead.
Then I was asking Dr. Johnson if he can comment.
Sir, during my presentation, I will be covering.
Oh, okay. Well, then we leave
finish
it till the end.
Then we will start. Okay. Let us finish the presentation.
Then we leave it to the end. That's fine. Well, yeah, then if somebody else has questions about this, we can discuss amongst ourselves, because Professor Reddy is, of course, not here to answer them. But please go ahead if there's any questions, any comments. maybe on the policy in India. If not, then we move to the next presentation, which is actually myself. And I already have been kindly introduced, so I can skip that. It makes it easy, and my presentation is not that long. So we do have some room for discussion at the end of the session to go through all the presentations and to address these comments that we just asked. But there might be indeed already ready-made solutions by Dr. Johnson B. or by the other speaker, Dr. Vava Mantri, because they probably go into Gracilaria cultivation and Gracilaria dura as well. So without further ado, then I'll start my own presentation. Share that. Can you see this?
Yes.
Yes,
We see
yes.
it on our screen.
Perfect, perfect. Okay, so well, I just called it the inaugural or first international conference and expo on seaweed farming, and hopefully we have more like this in the future. But that is up to the organizers. And firstly, I want to thank the organizers for inviting me to this conference. As was clear, we have a small company in Tamil Nadu, so I definitely have an interest in what is happening in India, and also want to play and become part of it, or we are already part of it. And for today, well, we have 4 speakers after Professor Reddy. That is myself, Dr. Alan Klitschle, who will be more talking about what he calls Phyconomy, and that is more on the numbers and statistics and what is produced, where, when, and what is needed. After that, we have Dr. Vava Mantri on technological interventions in seaweed farming, with special reference to India. Well, and I suspect this will deal with Gracilaria dura. And then the last speaker in this session is Dr. Johnson B., who will talk about integrated multi-trophic aquaculture and seaweed cultivation. And IMTA, as we call it, is also one thing that I very much support and think is the way of the future. But we will hear from Dr. Johnson B. at the end. So I'll start my own presentation, which is about mechanization in seaweed farming and looking at a more global scenario. And just to look at the seaweed industry, there is a lot of figures floating around, but we're talking about anywhere between 31 million tons wet weight that is produced, and 99% is coming out of Asia. And the rest is basically wild capture Europe, and we're talking about kelp resources here in Escofilm. If you look at the value of this resource, some marketing reports put it at 17 to 18 billion. Now, this clearly takes into consideration further processing, for example, snacks and other food products. But the raw material, you look at a value around 7 billion. So seaweed cultivation, about 30 million tons from Asia. And here on the right, you see this little graph of a little informatics, sorry, of the top 10 producers. And Professor Reddy already addressed this in his speech. India is not a world or global player yet. The one that is number 10 is Vietnam, which is actually very almost next door to you. So there is some work and catching up to do for India. Luckily, the government in India now has the vision to start putting money into this and developing this industry. But what I heard today in Professor Reddy's speech as well, there is no seaweed kind of subject or course as such in a university that's been taught as a separate subject. It's always part of a little thing. And that is where you have to make progress in start teaching this as a main field of science. So if you look at those 30 million tons of seaweed, the bulk is made up of 6 species. Sargassum, Capophycus, Gracilaria, Wakame or Undaria, kelp, kombu, and Porphyra or Pyropia, which is nori. And most of it is cultivated in China, Indonesia, Philippines, and Korea. And if we're talking about large-scale agriculture and mechanization, well, let's take a step back and see how this has developed over the years. And if we look or go back before the 1950s, and this can go back several centuries, seaweed was already valued as a food resource, but also as a source of medicine. And in Japan, you see the different pictures here. This is how they were cultivating nori or Porphyra. They were just sticking bamboo poles in the mud in an area where they knew there was Porphyra. The spores would settle on the sticks, grow into new blades, and they would harvest these sticks, and they had Porphyra. And then they would make their nori sheets, as you see there. And it was not until Kathleen Baker discovered the life cycle of Porphyra and exactly what happened there with the conchospores that can bore into calcareous substratum like oyster shells. They produce conchospores, and those conchospores can then be seeded on other substratum like nets or ropes or whatever. And that made it possible that actually real cultivation started to appear. And that was in 1949. So in the 50s, you get some startup of cultivation. Very rudimental, very small scale yet. But it started to increase, and there's more inventions started to appear to mechanize this industry. And the same thing happened, by the way, for kelp when they discovered or figured out the life cycle, how that works, and with other species as well. So if we're talking about mechanization, well, what does that actually mean? And if you look, and I call this Asian style, and I got the pictures from seaweed side from Professor Kairi, there's 8 steps in this cycle, and that is collecting fertile plants, getting the spores released that are growing into the conservalis phase in the oyster shells, then maintaining that, trying to get it fertile to produce conchospores. Then you can start seeding nets that you can store over a longer time to stretch your cultivation cycle, or outplant straight away into the sea, and then you have a harvesting cycle. If you see that in pictures, it still looks very hands-on. Only with the net seeding step on the right and the first picture in the middle on the left, they are the kind of mechanized steps where nets are put around these wheels that go through very shallow basins, and underneath are the oyster shells with the ripe conservalis phase that produces the conchospores. And then they can actually seed nets. But then further down, it is again hands-on putting this out. The real innovation is actually at the bottom, where they have started to design special boats. And these boats, like you see in the picture here on the left, bottom left, they are boats with bull bars that can actually go under the nets, and then on top of the roof of the boat they have an upside down lawnmower that is actually cutting off the seaweed as it goes along. And there's different variations on this, smaller little boats that go in, like you see here on the bottom right, with almost a handheld lawnmower that they pull the net over. And that's true mechanization. And in this way you can actually, well, harvest a lot more than if you have to do this all by hand. In kelp, the same thing. Once they discovered how this life cycle worked, where you have fertile patches on kelp or other kelp type of species, and you can release spores, grow them in male and female gametophytes, and then actually be able to grow these gametophytes, clone them and bulk them up. So you have basically a seed resource. And that can then be maintained in hatcheries, small scale, temperature controlled, light controlled, where you seed the gametophytes either directly on the rope, or you let the gametophytes fertilize themselves into small sporophytes, small plantlets that can be seeded on the rope and things as well. And here you see, for example, ready-made spools with this seed growing, and the plantlets are only 1 or 2 mil. And once they're big enough, like 4 mil, they can go out into the field and be, well, outplanted. But still, outplanting, here you see by hand, putting that seed string around a long line, put it in the water, and the mechanization here is that, okay, you have a boat, it lifts the long line, but there are still two guys here that are cutting off the seaweed with a big machete. So not that much mechanization. If we now go to the eucalyptoids in Philippines and Indonesia, there's a couple of species like Apophycus, Eucuma, and Gracilaria that are cultivated, and here you see immense amount of small patches where they have off-bottom cultivation. And there's all kind of variations on these systems. Is this mechanization? Yes, in some way it is, because you don't collect from the wild, you actually cultivate and in structures that you designed. But again, it is pretty much hands-on. And there is all kind of different systems with long lines, off-bottom cultivation, floating rafts, you name it. And this is all taken from Asia that was in the session here before, Anisha Hurtado. And also in India, same variation. It's long lines, floating rafts, tubular nets, and it involves still a lot of work. It's the same thing that my company is doing in Tamil Nadu as well, where we the Gracilaria again in tubular nets on long lines, and we're comparing the different systems, what gives the most yield, and that is of course dependent on where you are in India in respect of light, temperature, monsoon period, etc., etc. There is some mechanization, of course, going on, and you're all very familiar, I would say, or very aware of this. C6 Energy is heading that company, and they have developed this C combine. But in a way, it's still doing the same thing, putting seedlings into tubular nets. But the big advantage, of course, is that they can do that on board, seed these things, they go directly in the water, and also they can then take the lines out again when they are growing and strip them on the same boat and get the harvest. But otherwise, it is still a lot of seeding by tying the plantlets to the lines or putting it in tubular nets, different filling systems to do this, but very much hands-on and providing a lot of employment. And that straight away comes to an ethical question. So mechanization, it sounds great, but do we really want this in Asia? Because at the moment there is many coastal rural area family units depending on this for income, social inclusion, prosperity, and not only those family units, it's also the buyers, the warehouse owners, transporters. So a lot of jobs are dependent on this way of growing seaweeds. In Japan, which is very much mechanized, there are still 35,000 people working in the nori industry. If you look at the Philippines, 200,000. Indonesia, 70,000. So that is a lot of jobs depending on this way of growing seaweeds. If this is going to be mechanized, a lot of people would be out of a job. So that is a question, do we want to do this or not? And this is something I would like to address at the end of this session and want to hear your input on this. Now, if we look now to Western Europe, completely different story, because we don't have a really history of seaweed cultivation. Yes, we know seaweed has been used as food and all these kind of things, but it's always been wild harvest. But for us in Europe, it's becoming a more attractive proposition because fish stocks are dwindling. We have a lot of fishermen and they need something to do as well. So mechanization is the only way forward because labor is very expensive. Can't do it the way it's done in Asia. But that only works if we can make economies of scale. So you need large areas to grow seaweed and then you can mechanize. And that is not the case at the moment. Most farms that we know in Europe are anywhere between 1 to maybe 100 hectares. And 100 hectares is already a huge farm. Most people don't cultivate more than 5 or 10 hectares and that's it. And it is all artisanal by hand, which is great if, as a cottage industry, but if we want to take this seriously and want to scale this up, we need mechanization. And here you see some examples of photos of a project that I was involved in, where we started using 2D substrates to grow our seaweed on, and you get these nice carpets with a lot of seaweed biomass on it. Now, a lot of different mechanization steps have evolved, where they can seed long lines and also harvest long lines all in one system on a boat. You see some examples here. More examples here of different initiative and methodologies, where they have also some kind of a seaweed combine harvester, where they straight away seed brown seaweed on the nets, but also are able to harvest the nets with the same boat. And this, of course, goes on, and there's a lot of kind of, well, I would almost say kind of dreaming innovations put on paper that will never see daylight, and other things that look very plausible, as you can see here at the bottom, because this is based on a mussel cultivation system which can easily be adapted to seaweed. But if you look at capex, it is incredibly expensive. And then, of course, the cost of goods come into place, because seaweed biomass at the moment is not worth that much that will justify the capex spend. So that is the conundrum in the West, basically. Now, my own company, a seaweed company, we've also been looking at this, of course, but now trying to scale up, but step by step with the growth of the farm size. So it is low cost, low key kind of innovations to mechanize and improve yield. So what we have developed for the brown seaweeds, the kelp, is a system where we can indeed clone gametophytes, bulk it up, and then bring it out to where we have our farm. And we've developed an automatic net seeder, where you spray the seed on the nets, it goes through a gluing system, then to a fixing system, and straight away you can then the nets out and grow over a couple of months the seaweed. We have also done this with rope, direct seeding it's called, where you seed the ropes directly with a machine, and again through a gluing step and a fixing step, and then the spools with the seeded rope are collected, they go to the boat, and then roll them out again in your system. And again, this gives you a bit of the setup, and it's still hands-on. You need a couple of people to do this. It's not fully automated. Of course, the nets, and it also depends on where you are in Ireland, because it can be pretty rural as well. But you collect the seeded nets, and then they go to the site and IBCs or containers, and then we put them out. And how does that look like? A little bit like this, where you have loads of nets hanging there with the seaweed growing on it. Of course, not everything works as great as you see in the lab. So some nets have a low density, other nets have a good density. And then the other way with the fabric, where you spray the seed directly on the fabric, hang it out, and again, large biomass crop to harvest. And that brings me to the next point, which is harvesting and drying. And that is something that is problematic at this moment, because everything that's been done so far in Europe and the States is small scale. And that can be handled by hand, can be dried in the nice little units, which are 40-foot containers with dehumidifiers and vents and stuff like that. We did develop a net harvester, which is a small module that you can put on the boat with, in a way, a similar system with the upside down lawnmower that cuts off the seaweed. A much more simpler step is using a hedge trimmer and cutting off the seaweed. And drying, yeah, sometimes we have a few good weeks of good weather and a lot of wind, and here you see one long line with all this seaweed tied to a tree at the end of the field, up here on the top of the field, and within 6 hours, and the wind dry as a bone. But unfortunately, Ireland is known for its rain, and we don't have that much good weather, so we can't be relying on that. So the next step, when we grow about 100 or 200 tons of brown seaweed, how are we going to dry that? And that is another big problem that has to be solved. So to come to the end of my presentation, if we look at Asia versus mechanization, do we want that? And if you look at the Western world, then we are still at the moment in a situation where the capex outweighs the cost of the raw material. So yes, you can mechanize everything, have fancy boats that do everything, but they cost about $1 million. And the amount of seaweed, if you only do that on 10 hectares, is never going to pay for that boat, basically. So there's pros and cons. And if you look, and brings me back to the cup of ficus in India, because you have to compete with the Chinese, with Indonesia, with the Philippines, which is not going to be easy. There is already 30 million tons grown, but then looking at world population increase, food need, as Professor Reddy already showed in his presentation, yes, we need more seaweed, but do we mechanize it or do we stick with the same way of doing this? And in the Western world, yes, we want to grow seaweed. It is a huge demand, 10% growth per year, but mechanization with these boats and systems is only feasible if we start with concessions that are in the square kilometer, not in hectares. And that brings other problems on licensing issues, on bay management issues, etc., etc. So there's a few things that we have to solve. And that's where I would like to stop my presentation. Thank you for your attention, and we can either address this at the end of the session, then we continue with the next speaker, but if there's a small question, I'm happy to take it now. So are there any questions on this? Because we have still 5 minutes.
Yeah, Stefan, can you hear me? Alan Klitschle.
Yeah, Alan, I thought you were only coming in at the end.
Well, yeah, I got up early, couldn't sleep. It's a hot night here. Good day to hello everybody. Hello, Prash. Hello. Yeah, Stefan, you spoke about the morals and in Asia providing jobs, but there are quality of jobs too. Ian Nish has written a lot, and I've joined in with him, but the description of the labor in Southeast Asia of tying those seedlings on is drudge labor. And a lot of people really only want to do that type of work when there is nothing else. If there is work available in the service sectors, hotels, hospitality, people would rather do that work than do seedling work. And so some level of mechanization, I think, there and improving the quality of jobs, I think is really important.
Yeah, no, it's not black and white. It's just because I'm dealing with these Indonesian companies and I have my foot on the ground now. And there is some pushback, let me put it that way, of any form of mechanization taking shape. Now, that might be in a specific area, I don't know. Talking to Sri, I know that their focus is really offshore, further out. And looking at world growth, population growth, and that needs food, there is definitely a chance to increase production. And if that then slowly comes with increase in quality jobs in the processing, handling, whatever, then that's great. But it is a trajectory that will go in parallel.
Yeah, and yeah, just last point. But one of the things about the capex and all of the investment that goes in is balanced by the end value of the biomass. So if you treat your biomass as a commodity, for carrageenan extract, for instance, then the amount of investment you can put into it is very limited. But if you use the multiple use or biorefinery principle and extract many different, sequentially extract things of value, you can get a higher value for your biomass. Therefore, you can afford to put more into the production costs.
I agree, but we are not there yet.
I just wanted to put my 2 pennyworth in. And
no, that's very, very good. Anyone else who wants to join in and has a comment on this? We still have 3 minutes. If not, then we will proceed with our in the session, and you just heard him, Dr. Alan Klitschle, and I will introduce him first before it. You're going to present live, I take it, Alan?
No,
want to play
sorry,
the
I
video?
sent in. I don't have my presentation lined
Okay,
up here. I sent in a video.
Pravesh has the presentation, so that's fine.
Okay, great. Thank you very much.
Okay, so just then I'll introduce you. Dr. Alan Klitschle, he's a research fellow of the Verschuren Center for Sustainability in Energy and Environment of Cape Breton in Nova Scotia, Canada. And Alan began his career in Portsmouth in the UK, and he was actually at the time studying the invasive seaweed Sargassum muticum. And that is actually how I started to know Alan, because my own interest was in this at the time. And after a postdoc in the Netherlands, he made his way to an academic post in the University of KwaZulu-Natal in Pietermaritzburg, studying the subtropical seaweeds of the East Coast. Then another move was made to the University of Witwatersrand, where his first interest in commercial seaweeds were ignited with Taurus chemicals. Taurus is known from, for example, seaweed biofertilizers. And after some time, then he moved to Namibia. Again, that's where we started to interact more, Alan at the time, at the University of Windhoek to work in an academic and consultancy role at Multi Research and Consultancy Center. And this then led to the giant leap into the commercial world. Likewise, I've done myself on tropical carrageenophytes and temperate alginophytes at the Gusa Texturanta systems in Normandy in France. More recently, he found his way to the Verschuren Center via a small media enterprise in Nova Scotia, where he led the research group for on-land cultivation of seaweed for food and wild exploitation of intertidal fucoids and animal feed and plant products. Now, his current passion is Ficonomy, and particularly tropical seaweed Ficonomy. Alan, well, actually, Pravesh, can you start the presentation?
Hello, and greetings and good day from Nova Scotia on the east coast of Canada. I'm coming to you today with my co-authors Anishi Hurtado from the Philippines and Ian Nish from Indonesia. Back in the early 2000s, I used to work for Gujarat Coast, one of the largest processors of raw materials of seaweeds in the world. And it was there that I had the good fortune to become associated with Dr. Anishi Hurtado and Ian Nish. And 20 years later, our ties are probably even stronger than they were back then. One of the things that cemented that was in 2017, we co-edited a book for Springer that's called Tropical Seaweed Farming and Trends. And this provides readers with access to some opinions of the world's experts on eucheuma seaweeds. Back in 2020, Anisha and I, together with some other colleagues, got together to co-edit a series of special issues for Botanica Marina based on seaweed resources of the world. And so it's based on these experiences that I'm presenting to you today on Phyconomy and how cultivation of seaweeds can provide global benefits. Let me give you a quick overview. These really are my personal opinions on the urgent global phyconomic needs. Seaweeds are indeed remarkable, but we really do need to be careful of the hype and over-promising of what seaweeds of their different types can deliver. I would like to highlight the successes that seaweeds bring, but also that there are some gaps. These are not insurmountable, but there are gaps in the work that's required for seaweeds to provide their greatest societal values. I've used the word Phyconomy several times, and let me just describe what that is. Phyconomy is a branch of applied phycology. Phycology is the study of algae. And Phyconomy itself comprises a system of art, science, and technology as applied to production systems that yield crops of algae in its broadest sense, micro and macro, but we'll be talking mostly about seaweeds. So the prefix phyco pertains to algae. The suffix nomi is a system of rules and laws or knowledge about a body or discipline. So marine phyconomy, it bounces off the word agronomy. Agronomy is dealing with vascular plants in static managed soils, whereas marine phyconomy is mainly about macroalgae in unmanaged flowing seawater. So there are various forms of phyconomy. It can be simple as the guy on the right here, which is crude wild harvesting. I'd question the impacts on the environment and sustainability there versus the cultivation of seaweeds in the sea, farming the sea. This is adaptive phyconomy, or farming seaweeds on land in tanks, and we'd describe this as being precision phyconomy. Obviously a great deal more capital infrastructure and operating costs in the lower left hand side. But let's look at adaptive phyconomy. It's a low cost, low control approach to seaweed farming. And this is practiced where the biology of the algal crops is poorly understood and or where there are confounding variables. Nevertheless, this type of adaptive phyconomy can be carried out at an industrial scale. And what we see here are intertidal areas in East Africa growing the Eucuma capophycus seaweeds, and then bottom left and top right you can see the seaweed beds as illustrated in China and Korea. Bottom right there, it's not real yet, but this is how some of the seaweed farms of the future might look. Right in the center there, that really is the artisanal way of cutting select seaweeds with pairs of scissors. It does exist, but it doesn't lead to a great deal of biomass. Let's look now at the ages of phyconomy, taking the age of disorganization, which is the opportunistic taking of wild seaweed stocks, all the way through equivalents of the agricultural revolution, the industrial revolution, the scientific revolution, and we go through phyconomy as it occurs in open ecoscapes as well as then being highly mechanized and carried out on land. Where will we end up with these things? Of course, phyconomy comes with a cost, low to high, and that gives us either low or high control. If we look at marine phyconomy, whether it be tropical or temperate waters, this is open water phyconomy. There's relatively low control and relatively low cost. As we move up through artisanal and precision forms of phyconomy, we start to see enhanced use of technology and mechanization. At the pinnacle of control and cost, we have the equivalent of hydroponics and bioreactors in closed ponds and raceways, where the biomass is highly controlled, but the only way that it can be grown economically is if there are very high value compounds contained within. So along with phyconomy comes Phyconometrics. Phyconometrics are the volumes and values of seaweeds. And we have some reasonably good data here, just going back to 2005. There would be 14.7 million wet tons of seaweeds, the majority of those being from cultivated. Global production had increased doubled in 10 years, from 2005 to 2015, and we see 30.4 million tons of cultivated versus 1.1 million tons of wild harvested. So whereas the cultivated had gone up considerably, not so much with the wild harvested, remained about static. In terms of values, if we look at the predicted value for 2025, we see something around about $30.2 billion attributable to the biomass that is being produced from seaweeds. There are lots of companies that will sell you data about seaweeds and their values. We go from 2021 value of 4.1 billion up to 2024 9.1 billion, but the range could be larger than that, from 5 to 11 billion. But let's take FAO data that placed a value of $6 billion on seaweeds in 2018 from 12 million tons of seaweed. The important figure that I see there is that that comes from only 221 species of algae. So from amongst the diversity of seaweeds, really, according to FAO data, only 221 species are being used. We'll come back to that later. Okay, but what are most seaweeds being used for? Here we can see 2017 through to 2024, and what we've got is a breakout where we can see that most of those seaweeds are going to human food. There's some into hydrocolloids, and then it sort of flat lines around fertilizers, animal feed, and then some others. But the vast majority of seaweeds are going into the human food segment. Now, these data are from a paper of Alejandro Bushman et al. In 2017. And this breaks out global use of seaweeds and also where they come from. So looking at that data then, 2% of all of the seaweeds used in the world comes from wild harvested, the rest being cultivated. And then if we look at the regions where the majority of those seaweeds are being cultivated, that's in China, and then around the Coral Triangle, areas of Malaysia, Indonesia, the Philippines, Solomon Islands. What that study of Bushman et al. Also showed was that of all of those seaweeds, 5 genera dominated 98% of all of the cultivated seaweeds. So these were the cold water species or genera such as Saccharina, Undaria, Porphyra, and then some of the tropical red seaweeds, Eucuma, Capophycus, and Gracilaria. So altogether, 5 genera made up 98% of all globally cultivated seaweeds. So what we've got, numbers, Phyconometrics. There are around about 12,000 species of seaweeds around the globe. Very few of them, remember that number from the FAO, 221 are utilized. That's around about 1 to 2% of the diversity. We really have to improve that utilization rate. And furthermore, whilst there are some issues and problems with cultivation and production of seaweeds, we need to stick with the natural diversity and the variants, the cultivars. We do not need genetic modification of seaweeds. If we look at some of the trends in Ficonomy coming from Bushman et al., they performed a gap analysis, and there it became very indicative of the fact that in order for seaweed cultivation to become a major player in the world, there needs to be greater diversification of the cultivated biomass. Alternative species need to be selected, and via breeding and domestication, they need to supplement the existing cultivars. There's also a need to move into the more precision or advanced phyconomic activities of mechanization and incorporation of technology. But as with ordinary farming, as with ordinary agronomy, these crops are falling foul of fouling or epiphytic and boring diseases, all of which cause crop losses. These issues require considerable attention to support future phyconomic needs. So if we look at good phyco or agronomic practice, this is just taking things that have been learned on land, and carrying them through to phyconomy or cultivation of seaweeds. We have to remember that on-land cultivation has had millennia of time to develop, whereas the timelines for seaweed cultivation are in some cases decades and at best centuries. We must not rely on monocrops, and many of the seaweeds around the world are grown as monocrops. Furthermore, we should not rely on huge farms of one type of seaweed, the same way as we don't rely on one type of farm producing rice, potato, or other on land. We need diversification. We also need to consider crop rotation, and that's moving different species of seaweeds through the same area over time. We should also consider an old idea from farming practice, from agronomy, and that is to leave areas fallow, as in do not grow crops either at certain times of the year or have whole years without crop production. We also need to leave large areas untouched, and these are where the natural populations can develop, and these become the seed banks of the future. These are places where the future cultivars will be selected from and domesticated. We need precision phyconomy, as with agronomy, with applications of tech, both on land and in the sea. And furthermore, in order to make all of this come together, we need established, well-funded, long-term, dedicated institutes of Phyconomy, and these would be along the lines of the rice, the potato, or the grape boards that we see for land crops. They don't exist currently for seaweeds. So we think that seaweed farming is doing very well, but if we look at FAO data from 2020 and we break them out between China, the Coral Triangle countries, and then other countries around the world which produce seaweeds, we can see that there was very good growth up to 2015. But then after that, we can see that total production is flatlining. Yes, there's still some increase in China, but the rest of the world and the Coral Triangle is flatlining. If we look at the total production, we see that about 57% of the world's production happens in China, 34% in the Coral Triangle, and then just 9% in other areas of the world. So what does this mean? Is global seaweed production stagnating? A lot of that growth that we saw up to 2015 was a legacy because of markets such as hydrocolloids, and then other markets such as sea vegetables and feed additives have not been growing at the rate they were. If we break out and look at the hydrocolloids, so mostly agar, alginates, and carrageenan, data here from Bixler and Porce and Rudolph in 2016, we can see that carrageenan has enjoyed growth in the marketplace. But alginates and agars are basically stagnating. What is required are further innovative breakthroughs in Muse biorefinery technology. And I'll explain what Muse is in the next slide. But these will probably drive the next rise in seaweed production. It's innovation in order that there is more than a zero-sum game. And for example here, eucumatoid seaweeds, which are grown in India, are starting to be used for an expanding array of products which are beyond carrageenan, which are beyond hydrocolloids. So let's look at what is this innovative Muse process. It's multi-stream zero effluent. Let's take a single stream process. Seaweed biomass goes in to a high waste processing facility. There is one product, such as carrageenan and or let's say a biostimulant. Most of that seaweed biomass value is wasted. Whereas the multi-stream zero effluent process, or you would have also heard it referred to as the biorefinery, there is sequential extraction of products of high value from the biomass. There could be multiple product lines such as carrageenan or the hydrocolloid, agrochemicals, food and nutraceuticals, even petroleum replacements, plastic and surfactants. This ends up with little or no seaweed biomass being wasted. And so what we see then is that the seaweeds are able to fulfill their largest potential, producing products which are fresh and dried, animal feed, human feed, sea vegetables. They can produce seaweed concentrates for agriculture, feed supplements for animals, and biostimulants. There could be renewable chemicals, including carrageenan. These produce biodegradable films or super absorbent hydrogels, and even the biofuels. Biofuels have gone out of fashion a little because the cost of biomass far exceeds the value of these biocrude or fermented biofuels. Let's look at these on the scale. And can seaweed biomass be produced cheaply enough? Can it become a commodity such that biofuels, bioplastics, industrial suspensions, energy can be derived versus the higher value performance products, the biostimulants, the gourmet sea vegetables, and performance ingredients for animals and humans? That remains to be seen. Let's use an example. I've used this many times before, but it's one that I do like. When is a seaweed like a humble banana? Okay, if we look at the history, let's use the example of when is a seaweed like a banana. I might have overused this one, I do like it, but if we look at the banana, it nearly became extinct. It could still become extinct because its production is generally by colonial production and it is grown as a monocrop. Hence, it has become attacked by viruses and bacteria. I'll allow you to Google for yourselves, but there are tremendous negative human health costs and issues surrounding the use of chemical pesticides which keep those bananas in production today. If we look at seaweeds, and particularly the Eucuma capophycus type seaweeds, we can see that they have been propagated for at least the last half century by clonal propagation. They are extensively monocropped, although we see different color variants. Here, they're grown as capophycus or they're grown as Eucuma. There are reports of loss of seedling or strain vigor. They're not growing as well as they used to. And indeed, as with any crop, we begin to see disease, bacterial, and also other organisms living on the surface and within the seaweed that reduce its value and production. So what we have is marine phyconomy, okay, again mainly macroalgae in unmanaged flowing seawater versus agronomy, mainly vascular plants in static managed soils. But let's look at the agronomy versus phyconomy gap. We know that by the year 2050 we may have 9 billion, 10 billion people. We will have to double food production. Much of that food production will come from the marine environment. If we look at land-based agronomy, there are around 10 billion tons of product, mostly plants, and that volume is not growing. We waste a lot of that and we have to reduce the waste, but land-based agronomy, farming, is not growing. At the current rate of development, it will take 80 years for phyconomy to reach the scale of agronomy, i.e. for the amount of seaweeds grown in the sea to get close to this 10 billion tons. And that's where we have a tremendous shortfall between what is needed and what we can currently do. So, let me leave you with a few thoughts, and particularly this one here from a visionary. I had the great fortune of meeting Guillermo Garcia Blasi Reina. Sadly, he's not with us any longer, but he left behind a vision for a gravity-fed Atlantic Ocean water park to green the Sahara. And this is the type of integration of Phyconomy, this is seaweeds and microalgae, together with agronomy, growing plants using water from the sea in these integrated systems. And I really do commend looking at his work further, and the paper of Bushman et al. Does give you some insight into that. But let's look at it this way. Here's a thought. If we get it wrong, seaweeds or the algae were around billions of years before the Anthropocene. That's the one that we're currently in now. And guess what? They'll be around for billions of years after we've left. So if we don't get it right, you've all seen the recent UN reports about the state of the globe. We really have to do things correctly now. So some concluding comments. There are very few differences between the principles of agronomy and Phyconomy, and we need greater domestication. We only use 221 species out of 12,000. It's crazy. We do not need GMO solutions. This is not rocket science, but let's not repeat the mistakes from agronomy in the. So I put in here, thou shalt not steal, but do not distribute limited genetic crops around the world, which is what has occurred with the Eucuma capophycus species. Investigate indigenous diversity for their best applications. Look at what is in the local marine flora and pick and domesticate from those. That investment in indigenous efforts really is the mother of all invention. That's where new developments will come from. And then move away from the food or the gum commodities into the era of specialty bioactives and nutraceuticals from the seaweeds. So very quickly, final comments. Positive things are indeed happening, but we have to be careful of the hype. I'd say look at the rise of sulfated polysaccharides and see what good things they're doing in the world, including some antiviral properties. Promote the eucumatoids and look at phycostimulant applications from sustainably cultivated red seaweeds versus harvesting from the wild. Let's see Ficonomy move from being a hunter-gatherer into the precision practices. We're not out of the woods yet, but we're almost in a seaweed forest. So I'll leave you with that. And I'd just like a little bit of promotion here, just to point out to you that just recently there was a meeting at the University of Makassar in Indonesia called Tropical Phyconomy Coalition Development, TPCD1. This ran on the 7th and 8th of July, but if you go to www.phyconomy.org, all of the presentations, over 40 individual presentations, are there online. It does deal with the eucumatoids, but the principles of Phyconomy are spelled out by some of the world's leading phyconomists, algal biologists, and leaders in their field. Thank you very much for listening to me, and I wish you all success.
Well, thank you very much, Alan, for this wonderful presentation. And you might actually address the crowd yourself and ask for some comments and questions.
Well, thank you very much. And I sent in the video because I didn't think I'd be up at this time in the morning. But you know, the message that I'm trying to get across is seaweeds can do many wonderful things, but there are a number of people who are investing in some types of commercialization, which I think will never reap any benefits from that commercialization because the benefits have been overhyped. The actual deliverables, commercial deliverables, are not there. And the problem is that one bad experience for one type of seaweed will actually taint the whole industry. So we need to be careful. Seaweeds can do many wonderful things, but let's just keep it under check. And when we speak to other people about the potential, keep it in realms of reality.
Just to be precise, are we talking Asparagopsis here?
Yeah, if you Asparagopsis, I do think yes. There are a number of people who are growing Asparagopsis, and for whatever reason, they believe that there is the bromoform in Asparagopsis will cure all the ills of methanogenesis from herbivorous animals around the world. You know, that patently, it just biologically isn't true. But what it does, what it avoids looking at the literature about what other seaweeds can do. And there's a lot, the prebiotic effect of some of the fibers within many types of red, brown, and green seaweeds can achieve the same end results as Asparagopsis. Not maybe at the 98% level, but certainly at a lower level. And we haven't looked at blends, and you yourself, Stefan, have looked at the synergistic effects of mixing browns, reds, and greens to getting the best health benefits for animals and humans. We rather should do that, invest that money in that technology as opposed to trying to grow one form of seaweed. And there's not that many people online, but I'll just say, okay, follow the trail. It's like, you know, they always captured Al Capone because they followed the money trail and they ended up putting him in jail. With the Asparagopsis, bromoform is said to be the active ingredient. Look at what bromoform is as a chemical. Look at where bromoform may end up in the environment. And let's consider that you have, let's say, a multi-hundred tons production facility of Asparagopsis, and for whatever reason that system fails overnight, and how much bromoform would be released into the environment. What consequences would there be from that? It's like, you know, like
well, not only that.
I'll stop there.
No, but
you touched a nerve.
I hear. But not only if a 100-ton farm would fail overnight, but a 100-ton farm that is about 10 tons dry weight at 20 grams per cow per day, you could service a herd of 10,000 cows for a year. That's it. So
yeah,
you have to look at blends, and you have to look at other ingredients in seaweeds that bring the benefits, like you said, the gut health, the fiber,
absolutely,
antioxidants, all these kind of things. No, I just want to ask you something else, because in the beginning you mentioned 221 different species only domesticated or used for cultivation. Why is that? Because we have 12,000 species, and what I have seen over the last 20 years is the classical taxonomist has disappeared altogether.
yes.
And we still don't know what is out there. Yeah, we have given it a name, but that's about it. So shouldn't we not first take another step back, where we look at education, where we actually create these kind of jobs again, where people start collecting, looking at species, looking at familiarities between species, genuses, all these kind of things, and look actually what is in those species?
I couldn't agree with you more. I think it's very sad when you have a generation of scientists who deal with only the DNA extract of something that was collected by someone else and maybe sent to them in the post in a silica gel packet. We don't have too much time. There are still some classical taxonomists out there, and they need to train people in actually going into the field, collecting, being observant. But I think that why there's only 221, a lot of it is to do with convenience, and people in coastal areas, familiarity breeds contempt. People deal with the things that's closest to them and the easiest to utilize, and they don't delve off necessarily into the deep and look for other alternate species or even variants of some of the more common cultivars that we have. The industrial pressures to produce biomass tends to perpetuate activities in just using, it's the same old, We've always done it that way, so we'll continue to. But I think we really do need to look at those UN reports. The globe doesn't have too much time left to put things right. And so investment in the additional diversity of the benefits that seaweeds can bring it's not the only solution to the world's needs, but it is a big part of that solution. And if we don't understand the diversity, we won't get to the end goal.
No, I agree. Final comment from my side, Ficonomy board. And I already see that the chairwoman here is present, Anicia. She could run that. And set it up. But where do we go? Do we go to the FAO, or how do we set that up?
I think a lot of it has got to do with, and I'm hoping that in this meeting there are people from government institutions that can go back to their ministers. And I think the time is ripe that there's been a lot of positive publicity about seaweed, and hence the reason for this meeting and others around the world. There is a lot of positivity about seaweeds, but it needs to get to the upper echelons of government so that there can be investment. And then those governments can work with the UN. The UN does battle if it doesn't get the buy-in of other governments. So it's individually, all scientists need to work the way up the chain to the various responsible people in government departments and get their buy-in, because it's the sustainability of the investment that's required as well. The private sector can do some of it, but government needs to really show the way.
Nisha, you want to comment?
Yes, insofar as the FAO data is concerned, what they have is the data each country will provide them. So it's we have to go back to each country, because sometimes like the Philippines, if I may say, that the one being submitted is different from the industry itself. Like the government responsible for the statistics of the production of all seaweeds, with a majority of Capophycus, comes from the government. But if you compare it with the industry, the real production in terms of dry weight, it's different. So
I know.
So that's why we have to rectify really the actual data, so that we will be guided properly and will not be deceived. Because of course, what the FAO will say and will write in the yearly fisheries profile, we will quote and quote, and we will even use their data. But the root of that data comes from each country. So we have to be very careful with what we submit to FAO.
No, I agree, and I can give you an example straight away with Astruli in Indonesia. They have calculated on the basis of the raw dried seaweed and the amount of that you can extract out of it, that the numbers are about 75% inflated. So
yeah, I know
that gives you an idea. That gives you an idea.
Yeah, I know
too. Anyone else who wants to comment or say something, has a question for Alan on the numbers and the Ficonomy, or who wants to join the Ficonomy board? If not, then I'll thank you very much for your contribution, Alan. Very interesting. I learned a few new things again, so that is always good. Then we go to our fourth speaker in the session, Dr. Vaiba Mantri, the Principal Scientist and Divisional Chair of Applied Ecology and Biotechnology Division at the CSIR Central Salt and Marine Chemical Research Institute. Dr. Vaiba is currently Principal Scientist and Divisional Chairhead of Applied Ecology of the Biotechnology Division and CSIR Central Salt and Marine Chemical Research Institute in Gujarat. He has obtained his master's in botany with phycology as specialization from the Pune University in Pune, with distinction in 1999 and has a PhD in botany from Bangar University in Bafnar in 2010. He spent a brief stint at Ghent University, for people who don't know, that's in Belgium, at the Phycology Research Laboratory under CSIR Raman Research Fellowship in 2010. Dr. Manti has over 20 years of experience in applied phycology. He has developed technologies for seaweed farming of economically important seaweeds and has transferred 3 technologies so far to various industries. And I hope Dr. Vaiva will talk about Gracilaria dura as well. Dr. Vaiva, please go ahead.
Yeah. Thank you, Dr. Stephen. I'm audible?
Yes, sir. Yes.
Yeah, thank you. So let me share my presentation. Is it visible to all of you?
Yes, sir.
Yes,
It is
sir.
visible.
Thank you.
Just put it in
Thank you.
presentation mode.
Yeah, I have already put it. Is it on presentation mode now?
No. We still see the small screen with the little.
Yeah.
Yeah, that's good. That's it.
Now?
Yeah,
Thank you.
perfect.
So I have only 12 slides to talk, and I'm thankful to all the previous speakers because they have covered most of the global scenario, And I was asked by organizers to talk on technological interventions. And since we are from India, it is very essential to talk with reference to India because we have seen what all technological advances have happened and what technological advances should happen in India is a question today to me. So my talk is mostly on India, but I'll give 1 or 2 examples which are going to be repetitive. But let me start with a chronology because, like some of the speakers have shown how seaweed cultivation has initiated, how traditionally they were cultivated, and Dr. Stephen has shown that everybody, I'm sure, agree that the mostly technologically advanced farming is of Porphyra, and how the discovery of conchosylis stage by Professor Kathleen Drew has changed the entire scenario in Japan. So these are some of the chronological references with global perspective. Here, if you see, I have differentiated Indian context into 3 stages. First stage is, of course, initial efforts, then a middle portion, and third one is the most recent. If you see that one has to go back, to be very honest, the first paper on phycology in India has published in 1928 by Professor M.O.P. Iyengar. And I'm sure some of you must be aware about Professor Iyengar. He's called as a father of Indian phycology, and he was well connected with several international phycologists. Dr. Borgesen, who was a Danish prince and who visited India, actually gave an impetus to phycological studies. He visited a couple of locations in India, and that's how phycology, marine algae research started. And actual, breakthrough, one can say, was during the World War. And rather, many of the countries, phycology started due to the effect of World War because the supply was stopped and so many things happened. And small production of agar, indigenously produced agar, because they were using it for developing chlorella vaccine, and it was produced indigenously. So that was one of the biggest technological development for the country. Then our country realized, rather every country in the world realized, that they must, survey their coast and find out what is the resource potential. So we also had 6 to 7 such resource surveys in collaboration with various laboratories, and the pioneers were CSIR, CSMCRI, and CMFRI, with several state departments and local institutions. This data is available. Then we should remember a contribution of Dr. Thivi. Dr. Francisca Thivi was a visionary lady. She basically went to USA and worked with Randolph Taylor Professor Randolph Taylor, and she came to India and established a phycological school at CMFRI. After her retirement, CSMCRI called her to establish a school of phycology at Bhavnagar, Gujarat. She came, she did the first cultivation experiments in the country. They were between 10th of November to 28th of December 1963 at a place called Porbandar. Those who are from India must be knowing, it is a birthplace of great Mahatma Gandhi. And she showed basically that seaweeds can be cultivated. Okay. And then another person who has influenced the initial cultivation and processing was Professor V. Krishnamurthy. 14th August was his centenary year, his centenary birth, this thing. And he has encouraged the export of, seaweed resources to other countries. If you see a middle kind of development, there were several commercial seaweed landing centers were established. To be very precise, there are today 14 landing centers in the country. All of them are in Tamil Nadu and in Ramanathapuram districts. And then there were 46 cottage industries established. From Dr. Reddy's presentation, one can see that of those now 35 are there. They are cottage based. There are a couple of them who are big industries also. And then seaweed sap crop trials also initiated during this period. And our colleague Dr. Ramarao, who is now retired, he is the man who actually started this research in the country. These are the two phases, and most of them were of experimental or pilot kind of studies or production. Most recent, I would say, last 10 to 15 years, where commercial production of value-added compounds, and large-scale farming happened. Innovation, product diversification has come. Several linkages were established. Lot of awareness was created at several stakeholders, be it industry or education or research or policy makers everywhere. Skilling also was done. So this is the, in short, the chronology. Now I'm going to talk about two slides. As I said, previous speakers have covered. Technological interventions are largely happened in two sectors. One is seeding and cultivation, and second one is harvesting, where it is required also. I don't think I have to repeat it, but since I have made a slide, let me take a brief, time to explain you. As Dr. Stephen has said, Porphyra cultivation, it is one of the most technologically advanced. You can see that the picture is showing basically nets. They are wound above and seeding is happening on them. And in middle part, you can see that all those conchosylis germinating on oyster shells. And also there is a lot of technological intervention happened in Undaria farming, basically brown seaweeds, which are produced through through gametes. Then there are also good amount of research has happened on photobioreactors, including in India, and they are largely for cultivation, people have shown. But my own personal belief that photobioreactors should not be used for cultivation, they should be used for seed production. Okay, so these are some of the technological interventions in seeding and farming. Then comes the technological intervention in harvesting. Harvesting, as you might have seen from previous speakers, uh, the situation had changed. We were gatherers, like Dr. Allen said, and now we are farmers. So recent data of FAO also will tell you that more than 97% comes from farming, but still some amount of resource gathering is happening from natural resources. And you can see very rudimentary type of things are still used, and some mechanical kind of things are also used, especially in temperate areas, Ireland and other countries. In Tanzania, like India, most of the things are happening by a large number of labor force. Harvesting also, there is no mechanization. And some of the European countries, where harvesting is happening with the help of specialized boat and specialized cutting machineries. And in Japan also, there is a lot of mechanization in harvesting in case of Porphyra. Now, with these two scenarios, which are of global and discussed very intensively in the previous sessions, my question now is whether India needs this kind of mechanization. I am going to show you only research by my group, and there are some more groups also. They are basically doing research. I have specifically taken my examples where I can explain you in details. See, as a person, as a researcher working in India, we have a lot of possibilities. Like you all know that we are at level 13th position in as per the FAO statistics, which is very sad state of affairs. At the same time, it gives us a tremendous opportunity to grow. No other countries which are in the top will have that opportunity. Now, one also has to, I gave chronology purposefully so that people will know where we are. We can straight away should not think of cutting machines and this and that, which has been the practice in all the sessions and all the meetings which I generally attend and see people say we need this, we need that. Definitely we need that, but we need that at certain point of a time and not now. What we need is today, because we have a field station at Vandapam. I had a privilege of staying there for 3 years and working closely with the farmers. I realized that farmers are not very adapted to new technologies immediately. This is the example I'm giving you. We thought we were doing some research and we wanted to see how the production can be increased per unit area. And you all know that rafts, which are basically used in India and elsewhere, they are square or rectangular. And then we came up with this idea that we can basically use a triangular raft. And the advantage with this triangular raft is, I have written, one can read it. I don't have to basically read and tell. You need less anchoring. When there is a more current or waters are choppy, not very high currents basically, but where there is a disturbance, they are more stable structure. As some of you might be knowing that triangle is the most stable shape. I was told. I'm a biologist, but I was working with one of my student who is a mechanical engineer. And story is very interesting. I don't know those who are from Mandapam area, they might have seen it. They basically, fishermen basically go in the morning and collect shells, and lot of artifacts and ornamental things are being made from those shells. And the guy was basically using a harvester which was made from bamboo and was triangular. And they generally come to our our farming area and is to harvest those shells, and kind of things. Then I asked, they were local people. I asked my student to ask him first why he is coming only near to our cultivation area. Interestingly, he said, "Sir, we get more amount of diversity and quantity." And I was told later on, I also realized that the seaweed being a biological entity, they must be excluding some of the compounds or things like that. And then basically the shape of the harvester was triangular. Then I asked my student why this is triangular. He said, "Sir, that's the most stable structure." And the idea has evolved. We have tested it. You can see it at some scale. And we found that yield per unit area is more. One has to realize it's not a great technological innovation. Plant is not growing fast. Plant is growing same rate, but one can see that the harvest per unit area is much more. For triangular raft, you basically need 8 bamboo sticks, 4 big and 4 small for the diagonal area. But here you basically need only 3 bamboo sticks. So basically cost also can be reduced, and hydrodynamically they are better. I have also showed that we have also seen that a lot of drift accumulates on rafts. But here in a triangular raft, drift accumulation is only at the one of the corners, okay, not throughout the raft. And then some people might can relate that this arrangement you can see, the one which we have proposed, the first raft is only one, then two, then three, then four, like that. So if you see the birds, when they basically fly in the sky, they make this kind of arrangement because the first bird faces the biggest, what you can say, kind of disturbance, and then it is dissipated. So the other birds basically they don't have to face the same kind of action. And in this, we showed that the other rafts basically they are not exposed to the same wave action. So what I want to give the message here is there can be a small technological intervention. Technological intervention need not have to be a big, they have to be adopted by farmers. This is the message. I have not included another interesting thing I want to tell in this slide only. If you have seen Dr. Reddy's presentation, and probably Dr. Stephen also had shown, there was a mass mortality in India around 2013-14 of Kappa ficus, and lot of material got bleached and decayed and things like that. And we were wondering why this is happening. And at that time, I was at Mandapam. We used to go to everyday field. We realized that basically that was the time when there was no wind. The temperature was very high, things like that. And so there was a lot of stagnation in the water. And all the rafts, basically, most of the rafts, if I'm not wrong, there were something around 15,000 to 18,000 rafts at that time in the water. And they all were of the same growth cycle, means almost all the rafts are of same age material in those rafts. What had happened, my analysis says that because of high temperature, no wind, there was no water exchange. And rafts it's a small unit. There are bamboos, so water has to cross bamboo and then enter. And in Mandapam there is a practice that they use fish net below. So all this has created a kind of a ecosystem which is inside the raft, and the carrying capacity because of these plants growing was less in that small ecosystem. And then the idea came into our mind. This is going to happen every year, or we were talking about climate change. This is going to happen. How we can solve this problem? Then as many of you are aware, that there are so many cultivation methods. One of these is we call in India as a SRFT, single rope floating kind of a thing. It's basically ropes like this guy who is holding those ropes. The ropes have to be tied in the field the same way. So the ropes are basically hanging. The advantage with this kind of method is lot of water exchange happens. There is no barrier like raft. And we went and told farmers, please during this month, you don't use rafts, use SRFT method, so that your plantlets will get adequate nutrients, adequate light, adequate dissolved oxygen and whatnot. Farmers were said, very nice, we'll do, but they have not done it. We conducted 2 workshops at that time to make aware that this is the method by which you can do it, but it did not happen. Then we realized that although this method is good and things are like this, farmers are not going to do. Rather, they stop cultivation and revert back to the fishing. Then what we did is, we simply, if you see the raft, you need anchoring from 4 sides or 2 sides, basically. We asked them to take the rafts a little bit inside the water and ask them to remove 2 ropes, So what had happened? The horizontal raft became a vertical position. You understand? So with a small change, the water movement has increased, because in case of horizontal raft, there is no water movement. But in vertical raft, there is plenty of water movement. We did both these works on Gracillariae edulis. We have shown fantastic result. These publications are in aquaculture engineering. This triangular is in 2015 and the other one is 2016. I can send or people can read it. So what we wanted to show in both the research is the technological intervention which we want to intend to do should be very simple, and farmers should basically adopt it. Otherwise, having best technological intervention is of no use. Now, the next slide is about a device which we have basically developed, and we got a US patent also. Let me tell you that in Gujarat, when cultivation activity started, they were started with 3 by 3 meter raft. I was also part of it. It was a learning curve for us. The rafts we planted the rafts, came back. Next day when we went, all the rafts were on the shore. No raft was inside water because lot of wave action. These rafts could not withstand waters in Gujarat. Then we we basically introduce a method which is tube net method, and there were no tubes available at that time. What I did, I basically cut open the fish net, used 3 mm rope, put the material and stitched the rope and created a tube. At the same time, we just thought at that time, we just thought, let us do it and see, because Brazilians were doing tube net and Brazil was producing tubes. Okay. And then the problem with this method was good. It gave a best results than raft, and we adopted this in entire Gujarat. And then, since it is a rope and a fish nets are very, very expensive. We cannot afford to throw the net tube after one harvest. Then the question came how we can harvest, and that's how we designed this. But this is not of any use today, okay? Because what had happened in last 10 years, later on, lot of Gujarat is very entrepreneurship state. Lot of people in supermarkets, you can see that lot of tube kind of things are available to put your vegetable or material. So 2 or 3 industries have started now producing tube nets for commercial cultivation of seaweeds in India. All the 3 are from Gujarat. The cost of tube which we were using in the initially from fishnet was around 400, and then it came to 200 rupees or so per tube of 25-meter length. The cost of tube today is 40 rupees. So there is no need to have any harvester. This tube can cut open and can be thrown and recycled basically. So that way this has no significance, but we still have a significance, not for cultivation. But you see the advantage of we have published this also, the other work. You see, when when seaweed grow, the new growth comes out from the tube, and this new growth is free from epiphytes, and it has lot of multiplying cells, new cells. At the same time, material which remains inside is very old, good for any kind of product. We are talking in terms of 2 products in India. One is hydrocolloid, other one is a sap or a liquid which we use for agriculture, biostimulant. So if I want to get a good amount of biostimulant and hydrocolloid, I must use a old material which is not possible by any of the method. You take it by conventional farming, tie method, raft or whatever. Everywhere you get a big biomass, you have to use the entire biomass. The only advantage with this method is, this harvester is, you can segregate the material from apical tips and inner material, which is good in basically a product. Now I'm going to a very interesting research which we have done. This is the earlier one which I talked are vegetative propagations largely employed for red algae. I'm going to talk about a green algae. Many of you are aware, alva is one of the very important seaweed. It is unfortunately shown as a edible and having application in edible fields. More than edible application, I would say it has a alvan, and that should be the application. Now you see, there is a very excellent reviews very recently have come about what are the new varieties developed. basically for red seaweeds or brown seaweeds. There are, to my knowledge, there is no reference of green seaweed. Hybridization, breeding, and all kind of things are done in red and green. Brown. Now, in case of green seaweed, you cannot use vegetative fragments. Okay, you have to rely only on reproductive material. The reproductive material can be either gametes or zoospores, or third, I could say asexual zoospore. It is a very different type of life cycle. Will not go into third type. We'll basically talk only two, gametes or zoospores. All of them have an ability to regenerate into a new plant, morphologically identical, and give you everything what you basically need. Now, if you want to fuse, if you want to develop a breeding technique, develop a new variety in green algae, especially in alva, I'm talking in alva, you basically have to fuse the gametes, and then you can basically develop a variant and select the strain. If you see, as I said, every part of it has a regenerative capacity. So basically, you can induce the sporulation. There are methods available, very well researched. You can get a gametes zoospores, allow the gametes to fuse, and then basically try to get a variety. But what happens beyond certain time, they all get settled down, and it is highly impossible for you to segregate which one is fused and which is not fused, because they will start growing, germinating. In another few hours, cell division occurs. So if you want to segregate unfused from fused, highly difficult. There are some methods shown here. I'm not going to talk about them. I'll tell two ways. Some of the methods where one has to sit under a microscope, with a microscope, observe the whole procedure, pipette out the selective one which have hybridized, where fusion has happened, and it's just like in vitro fertilization for producing human babies. Same way you have to select and do it. Highly precision, good amount of skill is required, very difficult. Only study which I found interesting and published in Botanica Marina in 1976 is, you can see this a device they have developed. It's very simple. It's a centrifuge tube, plastic centrifuge tube. They have put two arms, another burette or pipette kind of a thing. They put gametes from above. The light source is below. You have to understand one basic difference between gametes and zoospores is, or a zygote is, gametes are phototactically positive, means they will basically go towards light, and zoospores are phototactically negative, they will go away from the light, and zygotes also will go away from the light. This is the difference we should basically use to segregate this. But the device which they have shown here in 1976 paper, the light source is at below, that means your gamete should come below, and then after fertilization, whatever zygote will form should go away. But you have to understand the physics also, because gametes are very small, less than 5 micron in length. When they fuse, they will form a larger body. It will have more gravitational mass. So even if it is negatively phototactic, it will tend to come and settle down where you already have a gametes. So although technically it's okay and published, practically it's not possible, because your gametes and your zoospores all will come down. Gametes will come down because of light source, and zoospores will come down because of its gravity. What we have done, we have developed a very simple design, a simple.
Dr. Faiba, just to keep in time, we are already.
Yeah, I think I have only one slide after this.
Okay, perfect.
I'll finish. So you can see this is the method which we basically, this is the cultivation practice which is developed in India. This is the box where you can see we have put one bulb, and we have made this into two compartments. One is white in color, another one we have given totally black. We have put some kind of test tubes. You can put here gametes, which will always tend to remain up in upper box, in upper compartment, which is white, and zygotes will go down. Below I have shown we have done a flow cytometric analysis. We have shown hourly basis how the population is changing. And this is one kind of technological innovation one can implement for developing various, hybridization kind of a study and developing improved varieties. Okay, as I said, I will talk only briefly, I think 2 or 3 slides. Dura is one of the very important species. We have several of publications, and you can see the question here is, Dr. Stephen, which method has to be adopted? There are 2 methods, monoline and tube net. You see, both methods are good. We have tested them for 2 years. Always we think that we should use one, which is wrong. Both methods have their advantages and disadvantages. Monoline basically gives only one plant, which is tie with the tie method. In tube net, there are mass of plant which is gone inside the tube. This is of basically fluid dynamics we have studied. We have shown the nutrient availability and everything is better in terms of monoline. The basic difference between monoline and tube net is very less biomass is required to start with monoline. Very huge amount of biomass is required for tube net. If you see growth rates and if you see kind of multiplication event, you see that the fold increase in the biomass is much more in case of monoline. So what one can do is, based on the season and based on the time, farmer should use both the methods in tandem. Another very interesting study we have done, when we made a tube net, we wanted to know whether this diameter should be the same or can we have anything less diameter, more diameter. So we have took 2 different diameter tube nets. We have shown here a smaller diameter is the better, because smaller diameter allows plants to grow much in the outside. So I'm not going to talk here. Also we have done CFD analysis and shows why it happens. I think this is my last slide. We are talking about seaweed farming, a large scale, and you have seen from Dr. Reddy, government is coming. From where seed will come? So we have done a preliminary study in 2015. Apical fragments were basically used, and we have produced the seedlings, and we have shown that these seedlings can go to outdoor, a kind of nursery, which is of course now done at Mandapam at very large scale. We got a best facility available, and we have outplanted them, did field cultivation, and this can be a sustainable application. I think this was my last slide. What I want to conclude with this, India definitely need a bigger and greater mechanization and innovation, but at the same time, we also have to see what can be done in the current scenario by which farmers keep getting same benefits, little more benefits, and then we can slowly move on to next kind of innovations. I thank organizers for giving me this opportunity. I thank Dr. Kannan Srinivasan, director of this organization, for nominating me for this event. And I also thank all the directors, past directors, who has always helped me, to do some time of a different kind of a study. By the way, all the studies which I have shown are from CSIR studies. They are not funded by any DST, DBT kind of funds. They are done through our internal funding. Thank you very much.
All right, thank you very much, Dr. Vaiva. And I must say, very interesting talk. Pity that in the last 3 slides that were, for me, the most interesting, that you had to hurry up. So a quick question on that, because you said the farmers could use or should use actually both systems, and monoline and tubular net. Is that depending on the time of year, monsoon, or on temperature? And what is your recommendation?
I'll explain you. I'm going to talk about Gujarat Coast. This study is particularly applicable to Gujarat. In southern coast, especially in Tamil Nadu, one method can be used, which is basically they are using. See, in Gujarat, what happens in initially or any region, after monsoon, when you start, you have a scarcity of material. So in case of tube net, you need a big amount of material. Like in case of Gracilaria dura or Edulis, which you are interested in, you need like a 10 kg of material for one tube of around 20 meters in length. You don't have. Probably a farmer has only 10 kg of material with him. He could conserve during the entire monsoon. So he can basically make one tube. But if you do monoline, he can make 10 monolines because every monoline requires something around 1 or 1.2 or 1.5 kg of material. So initially, you basically should start with monoline because the nutrients are very high immediately after monsoon and the plants can grow. But as the time progresses, wind action increases, especially in the west coast. By the time farmer has more biomass, and monoline does not have protection. So once the biomass grows after 30 days or 40 days, it becomes heavy and it drifts out. But tube will not allow the plant to go away. So the farmer should change the method after January, February, and should start using tube net.
Very clear. That is good information, I must say, and very logical as well. So the monoline could be used also to create biomass to feed the tubular nets later on as well.
Correct.
Fantastic. Anyone else with a question for Dr. Vaiva?
Just ask a question, please. Hello, how are you doing?
Hi, Alan. Thank you.
Nice to see you.
Yes.
With regard to the density within the tube net, do you ever see that as being a situation that creates any form of disease or bacterial breakdown because of lack of oxygen exchange or gaseous exchange in the center of the tube?
Okay. My experience with the tube net is only limited with Gracilaria edilis and Gracilaria dura. And we never experienced this kind of thing because we were always doing it on Gujarat Coast where there is a huge wave action. And the material which we put is not that dense. So probably in case of material where they put very dense and then there is no wave action, this will happen, definitely happen. But epiphytes are more in case of tubes. We have done some studies. We have not yet published, but epiphytes are much more. Epifauna is also more in tubes because it gives a protection, for them to grow. But in monoline, there is no such problem.
Okay. And then one last question. I know part of the answer, but in terms of going from simple forms to more complicated forms of growing seaweeds, do you see the benefits of adding any fertilizer and or biostimulants to the seaweeds themselves when they're growing in the ocean?
Yeah, thanks, Alan. As you might be knowing, because 2 days before only we got our paper accepted, thanks to Dr. Alan and Dr. Hurtado, who pushed me to take this. There is a huge, tremendous benefit of using seaweed biostimulants on seaweed growth. We have tested it at least for 2 seaweeds, and we are doing it for another 3 more, which work is progressing. And I learned from Dr. Allen and Dr. Hurtado that there is a huge opportunity to do this. But I would see it, what Alan is asking, whether these fertilizers can be put up. I would rather say, Alan, that we should not use it as a fertilizer, but as a pre-treatment, because that's the area where you have a huge scope and it is just started. This, I don't think many people have done except Dr. Hurtado and couple of recent studies by others. We must use this opportunity.
Thank you. Thank you.
With pre-treatment, you mean dipping
Yes,
the seedlings before you put them out?
Yes.
Yeah.
Exactly, that's the idea. Stefan, actually, insofar as the tube net growing for seaweed is concerned, Dr. Mantri, I tried it in Ficus, but not on Alvarezii. It's a different strain of Striatus in Zamboanga. It's only a 30-day period of 30-day period of growth. It was so robust. They're all growing outside, but the thing is, inside at the middle, there is the problem. because of the stacking density is so thick, there was the tendency that they fragmentize and even the occurrence of ice. And sometimes there are barnacles already. Probably one of the reasons why it resulted to that kind of biomass was that, remember when you gave me that tubular net intended for Gracilaria, but I used it in Capophycus. Yeah, and the mesh and the diameter was so small. Well, there is an initial very encouraging result, but I think the mesh should be bigger for Capophycus than the Gracilaria. But there is a potential there actually in tube nets.
Yeah, see, I will tell you, I would like to give 2 points to you, Dr. Hurtado. By the way, I have asked Monica to give you some more tubes. She probably will be visiting your country under some fellowship. So she may help you with different tubes. And which I gave you were, yeah, so which I gave you were mostly, basically are for Gracilaria. See, I'll tell you, when we use this tube net and Tamil Nadu, they were of no much use. Tube nets is possible, means should be used only in the waters which are highly choppy, because as you rightly said, nutrient exchange is not going to happen inside, in the core area. So tube net should be used only in the areas where lot of wave action is there, so that this problem will not come. Philippines water to me is already a stagnant kind of a water. I don't think it's an island country. Your country is an island country. Waters are mostly stagnant. You have not seen Gujarat Coast, such a huge wave action. When there is a high tide, no, you cannot put anything inside. Such places, this tube net are best, and this problem also will not come.
Okay,
Yeah.
that's
If
good
I can sum
information.
this up for you both, it very much depends on the species, the growth rate, because it creates then also problems in the middle, and the mesh size of the tubular nets for the species. And that is R&D, trying it with different mesh sites, different species, when to stop with the growth, because if it becomes too big, then you get the anoxic layers inside, you get your ice disease, you get your barnacles, and that's just trial and error.
See, I'll just take a moment to show you again this slide. You see, I have asked my student to take a cross section. I don't know why it is not coming. So if you see, it's a fully grown Gracilaria dura tube net, where a cross section also shows you a good healthy growth in the middle. Anyway, people can see, basically the publication is already there in JPH. So there is no problem. As Dr. Stephen said, it depends on species also.
Yeah, I totally agree with you, Dr. Mantri and Stefan.
With these comments, we wrap this up and go to our next speaker and the last speaker in the session.
Thank you.
Dr. Johnson B. Dr. Johnson B is working also at ICAR, Central Marine Fisheries Research Institute, CMRFRI, in Mandapan Regional Center as a scientist since 2010 on marine fisheries and mariculture extension and economics. He completed his master's and his PhD in agricultural extensions during 2002 and 2011 respectively. He received the Indian Agriculture Research Institute Senior Research Fellowship for his PhD program and joined in the Agriculture Research Services on November 14, 2009. He also has won the Young Investigators Award in the International Conference on Advances in Algal Biotechnology 2016 at the VIT University in Vellore. So, Dr. Johnson, please go ahead.
Good afternoon from India. Am I audible, sir?
I can hear you, but the sharing is not. Yeah, there we are.
Your
Perfect.
slides are visible, sir?
Yes.
It is visible now, sir. It is visible now.
So at the outset, I would like to thank all the speakers for an excellent presentation. I am the last batsman in this session. At the outset, first I would like to thank Dr. Pavesh Pradhan and his team for the wonderful job they are doing behind the screen from the day one we have been discussing about this event. Thank you, Pavesh Pradhan. I would also place on record my sincere thanks to my director, Dr. A. Gopalakrishnan sir, and the head in charge for nominating me for attending this conference. I'll be talking in brief about integrated multi-trophic aquaculture. The Central Marine Fishery Research Institute is under Indian Council of Agriculture Research of Ministry of Agriculture and Farmers Welfare of Government of India, as doing pioneering works on seaweeds from 1970 onwards. One of the innovation in the seaweed research is integrating seaweed with cage farming, because we are promoting sea cage farming in our country. So this concept is mainly for economic prosperity and environmental stability. So you see this graph, it's quite evident that in 1970s, aquaculture sector was relatively insignificant. But today you see it is a sunrise sector wherein the production is almost more than the capture sector. When we expand the aquaculture, one of the issue we have to face is unregulated and bad management, which will definitely create negative impacts on the environment and the portion of the society. In such situation, engineering aquaculture, that is to increase the environmental sustainability and economic stability, this concept of IMTA is very important. And in 2004, Jack Taylor, who combined the integrated aquaculture and multi-trophic aquaculture, the term integrated multi-trophic aquaculture. As you all aware, Dr. Thierry Chopin is the father of this IMTA concept. And there is a basic difference between polyculture and IMTA, because in polyculture, the different organism has the same biological and chemical process, whereas under IMTA, the different organisms have different biological and chemical process, but at the same time, they balance each other. That is the uniqueness of IMTA. So to give a brief definition, it is a combination of pet aquaculture species, it may be either finfish or shellfish, with organic extractive aquaculture species, it may be a shellfish or herbivorous fish, and inorganic extractive aquaculture species, that is seaweed, mainly for environmental stability, that is biomitigation, economic stability, that is risk reduction, and finally social acceptability. So there are three components in this. The first component is sea cage farming. As the fish catch is dwindling, so the income is also dwindling for the farmers. So at the same time, the demand of the fish is increasing. So with this background, the ICR Central Marine Fishery Research Institute is developing technologies for seed production of high value finfishes, shellfishes, and the farming techniques. The Mandamam Regional Center, where I'm sitting in country, this is the first time we have bred the cobia and silver pampano, the high value marine finfishes, and their farming methods, which has been successfully demonstrated and being currently adopted by the fishers in all over the country. This is to show the picture, the cages, the 6-meter diameter cages. The depth varies from place to place, and here it is 3 to 4 meter depth. And here mostly they're farming cobia. It is Rhachycentrum cannadum, and it has an excellent growth rate. So you see 2 to 3 kg in 6 months, 7 to 11 kg in 1 year of culture period. So a tremendous growth rate, and farmers used to get 2 to 3 lakhs as a profit. So this in Indian rupee. And the second thing is seaweed farming. As a lot of the entire day we are listening about the seaweeds. India has a very good potential for seaweed farming. And almost more than 1,000 families are involved in this farming, because it is a very good option for the women empowerment, and also providing one of the important diversified livelihood option, especially for the fisherwomen in this region. And here the collection of seaweed from natural seaweed beds is also taking place in Tamil Nadu, that is in Gulf of Mannar and Park Bay region. Mainly they are targeting sargassum, turbinaria, gracilaria, and gelidella for agar and alginate and for biofertilizer purpose. As you are aware, these 4 things are very important factors As Dr. Vaibhav was mentioning, in 2013, the temperature and along with there was no wave action, and that lead to the entire crop loss. So that you see, these are the important factors for seaweed cultivation. And bamboo raft method is wherever the calm and shallow it is being adopted, and monoline method wherever moderate wave action, shallow depth, and presence of less herbivorous species, it has been adopted. And these are some of the images of seaweed farming in bamboo raft method, wherein fisherwomen are involved in seeding and men are involved in launching the rafts into the sea. And these are some of the activities wherein fisherwomen are involved. You can see. And as tube net method, wherever higher wave action, this is ideal. And this is very excellent, and it is doing well in Gujarat Coast and Andhra Pradesh Coast. And native seaweed species, yes, there is a technology available for Geldila cirosa, bottom culture method, and for Gracilaria edilis. There are 3 methods which is being there, and in some places the adoption is also there. And Gracilaria dura and Hypnea valencia, these are some of the field cultivation technique. It is some are in pilot scale and some are ready for adoption. Gracilaria debilis. And finally, the edible seaweeds. The tank-based cultivations works are being undertaken, especially Ulva lactua, because in India, seaweed as the human consumption has to be promoted, and this is one of the area where a lot of works is being carried out. So as on date, the Capophagus alvarezi red algae is being farmed in our country. The reason behind is like it has a fast growth rate, and also the fisher family, they are getting a very good revenue, and the crop duration is also 45 days. Whereas native species in places like Lakshadweep Island, Andaman Island, and in Gujarat is being promoted. There also all our trials showed a tremendous growth, especially in Lakshadweep has shown a tremendous growth rate of about 10%. So in coming days, native seaweed species farming also will place on record in our country. Recently, Government of India has launched a scheme, Pradhan Mantri Matsya Sampada Yojana, with the aim to increase the seaweed production from the current level to 11.2 lakh tons by 2025. They have provided some government assistance for fishers, fisherwomen, and for different community. And this is to just show how government is very keen in promoting seaweed farming in our country. And the third component, mussel farming, it is popular in Malabar area, especially in Kerala. There's a farming technique for Perna verdis and Perna indica. And there are different culture methods are available for mussel for deep waters and intertidal and shallow waters and bottom culture method. And the most commonly adopted practice is rack culture, wherein the seed material in a meter of 0.75 to 2 kg will yield 5 times growth in the period of 5 to 6 months. So integrating these 3, which leads to the concept of integrated multi-trophic aquaculture, the idea of biomitigation along with increased biomass production. And this is how we did our trials and our demonstration, which we all completed by 2013 to 2017. And currently, the farmers in Tamil Nadu coast, they are adopting this technique. And in other places also like Gujarat and Visakhapatnam, this technique and in Lakshadweep is being adopted. And I will give in brief in what way we have did our demonstration. We have integrated 16 raft, which is 12 feet by 12 feet size in a 6 meter diameter cage. And we compared the yield along with non-integrated one, that is cage alone and seaweed alone. And this table, you can see a farmer who is having one cage integrating 16 bamboo raft for 4 cycles with 1 cycle of fish production. he could get an additional revenue of 50,000 rupees in Indian rupee. It roughly works out to works out to 675 US dollars. So such a lucrative option, seeing is believing. When this was observed through our demonstration, farmers themselves are undertaking this activity because the seaweed yield almost 60 to 65% increase in the seaweed growth when compared to the control one. And this also helped after our 2013 crop loss. This particular technique helped the farmers wherever it is possible, who are adopting, they could get additional yield through this technique. And we also did a carbon sequestration potential through CHN elemental analyzer. And we could find the average carbon content is 19.92%. And per ton of dry weight of Kappa ficus, the sequestration potential is 19 kg of CO2 per day. With this, we were able to compare the carbon sequestration potential of seaweed cultivation with and without IMTA. There is an addition of 174 kg of carbon sequestered through this integrated multi-trophic aquaculture. So hence, seaweed and IMTA is one of the climate resilient aquaculture technique, as you all aware, which is very essential to mitigate the ocean acidification. And indeed, it is a green technology without involvement of energy, fertilizer, and chemical inputs. And moreover, it is not a labor-intensive activity. Another one serendipity discovery is like in the seaweeds, which are grown under the integrated condition, had more number of apical portion. That is 90 to 100 numbers. When we compared with the non-integrated one, it was only 30 to 40 numbers. The advantage is when we use this as seed material for subsequent crop, the plant is ready for harvest within 40 days. So we can still reduce the crop duration. And this is how it also benefited the farmer. And these are some of the images wherein the cobia and seaweed harvest, where the fishermen were doing, we were participating in this harvest. And there was 20% increase in the fish yield also. So there they could get an additional revenue of around 1 lakh in Indian rupee, which works out to around 1,350 US dollar. So put together, when we add what is the additional revenue in fish farming and seaweed farming, a farmer could get 2,000 US dollar. So which is a very good economic returns. And that is why the adoption rate is also very good for this particular practice. And absolutely, there is an environmental benefit is there because the biochemical analysis of water and the sediment from the integrated raft to the cage revealed that there is a mutual benefit for the seaweeds and the fish. And we also not only doing Kappa ficus and with the gracillary release, whichever farmers are interested, they are integrating cage with gracillary release farming. Here we could get 10-fold increase. That is the 5 kg of seed material per raft yield at 50 kg in a duration of 45 to 50 days. And they were doing for 4 cycles. And this is also being encouraged under IMTA condition because there is a very good growth under the IMTA for gracillary release. And recently, this was published in our dailies, in the New Indian Express, and the website also. Our Central Marine Fisheries Research Institute from Kerala, Kochi, there was a bumper harvest of green mussel. They could harvest 1 ton of green mussel from 150 strings, which was integrated with 4 fish cages. So the individual mussel grow to a size of 72 grams, which is a successful growth rate in mussel farm. So this is also evident how the mussel and seaweed have an additional gain in the growth as well as income to the farmers. And I also place on record this, one of the farmer who is continuously adopting was recognized by the, got a state level recognition by getting a best farmer award. He received best farmer award in one of the state level Kisan Samriddhi Mela organized in 2018. Initially, he was very skeptical about this technology because already in 2013 there was a crop loss. But when he could see there is a increase in the seaweed, almost double the yield in the farming of seaweed alone, he could be encouraged and he continued the adoption. That paid a reward for him. In continuation, in 2020 also, he got Best Open Seekage Farmer Award. His name is Mr. Mohammed Mugu from Monekadu, Ramanathapuram district of Tamil Nadu of India. And it's a very good recognition for this technology. So to conclude, definitely the integration will favorably generate additional revenue through increased yields of seaweed, finfish, shellfish, and mussel. And no doubt it is a biomitigation along with the production. And the third one, very important, it is a natural crop insurance, because if one fails, the other will definitely will help the farmer. And definitely by effectively controlling the organic and inorganic pollution in the natural open waters, it ensures ecological balance, and definitely it is an eco-friendly technology. And it's also one of the significant mitigating measures for the adverse impact of climate change and earns carbon credit to our country. So with this, I'd like to thank each and everyone for your kind attention. Thank you, one and all.
Mr. Kran, you're not audible at this point. You're not audible, Mr. Kran. Maybe you have to unmute yourself.
I just did. Sorry, I'm already firing away. But yeah, no, thank you, Dr. Johnson. Very, very interesting talk, I must say. And you said something that hit the nail on the head. Seeing is believing. And you have these several farmers with winning best awards, best cultivation, the best production, and that is of course the proof to show this concept is a no-brainer. I mean, this should be integrated in anything that we do with aquaculture research. First of all, I want to ask the floor if there is any questions for Dr. Johnson.
Stefan, yeah, thank you very much, Dr. Johnson. With regards to seaweed cultivation, I think diseases are on the rise, but do you see that the integration with fish and mussels as being a way of keeping the area as pristine as possible, and so all trophic levels benefit healthy? All of the fish are healthy, the mussels are healthy, and the seaweeds are healthy. Do you see a correlation?
Thank you, Alan, for your compliment. Yeah, definitely. Whatever the yield we have seen, that is seaweed, fish, and mussel, it is absolutely very healthy, and the product is also getting good price because of the very good healthy condition that we have witnessed. Yes, Alan. Definitely, it is a healthy product.
Okay.
Because this might be a way to mitigate disease issues, eh?
Exactly. Yes.
Yeah. One question, and this is even one step further than IMTA. Is there a possibility where you can actually use your seaweed as an ingredient to feed the fish? Because if you can do that with either the Gracilaria or the Capophycus or whatever seaweed you're growing, then you really start to get carbon credits. Because now you don't need to use other resources, tapioca starch or soya, for example, from other regions, which are food crops. And in that way, you can keep the carbon in a cycle going. Have you ever tried something with that, with fish feed and using seaweeds?
Dr. Stephen, actually, certain industries are working in this area. They're working, they're preparing aqua feed based on seaweeds, but it is in the experimental phase. I hope in coming days, the aqua feed based on seaweeds will be there, and definitely it will be an answer for earning still carbon credit to our country. Yeah, the work is in progress.
Great to hear. Any other questions? Or actually any other questions of any presentation that you've heard this morning? And I still have my ethical question for you, what you think should happen in India. Do we continue with mechanization, or like previous speaker said about the triangular shaped rafts, small technological developments, but still keep that as a, yeah, I must almost say traditional way of growing seaweeds? So any questions you have or any answers you have, please fire away.
Shall I answer, Dr. Stephen?
Yes, please go ahead.
As on date, the farming is being carried out by the fisherwomen, most of the artisanal fishermen in near shore. So for them, the current practice of adopting either raft method or monoline method or long line method is advisable, and it will be continuing. Whereas for mechanization, definitely the entrepreneurial model has to be demonstrated and its full economic has to be shown, proven, because there are a lot of issues which has to be sorted out. Once if it is a successful model, then definitely that can also be adopted, provided if there is a proper legal or a proper policy guidelines is there for that. This is my opinion in brief.
Yeah, no, much appreciated. So in a way, yes, but not yet. There need to be a few steps put in place first to actually show and demonstrate it is viable in that way, and creating the high value jobs as well, of course.
Yeah.
Anyone else wants to comment?
I just wanted to encourage people like Dr. Johnson to continue searching within the Indian diversity of seaweeds, the seed stock in the natural environment, to look for new species that can be brought into cultivation. Capophycus was introduced. It has been successful to some extent, but the production of Capophycus in India has gone down significantly since the warm water events. But there could well be further species that could replace Capophycus as a crop if the focus wasn't necessarily on the production of carrageenan. So please carry on with the search for new candidates for cultivation.
Well, Gracilaria dura is obviously, in my opinion, the one to go for, especially if you look at the world market. It's a new species in a way for cultivation. They have experience already in India. Dr. Kanis also done this work on dura. Again, a no-brainer, in my opinion. Because starting to produce carrageenan and having to compete with the existing powers to be, especially with the big gorilla around the corner, China, that is dominating the market.
Yeah.
That's going to be a hard kind of.
Absolutely, yeah. And just supplying a commodity, the only thing that you can compete on with commodities is price.
Well, and we know who's going to win. Yes.
Yeah.
Yeah, Dr. Stephen, I would like to share one thing. You said that you are interested in Gracilaria. You think that Gracilaria dura should be the next species. We also
looking at your own slides of the Moroccan
so we also
of the
strongly believe. But let me tell you another issue with this. All these seaweeds which we are talking today from Indian context has already a price fixed. In case of Gracilaria dura, there is no price fixed. No industry has so far fixed the price. So if your industry is interested, we would be very happy to work with you on this.
Yeah, well, it has a superior agar quality and is at par or even better than the Gelidium. So there is definitely a market for this high end, and then prices will be matching that as well on the raw material. Then it becomes a very attractive proposition for a farmer.
Correct.
Any last comments, remarks? Because if not, then I'm going to close this session. Well, if not, then I would like to thank all the speakers that we had today. Dr. Vaira, Dr. Johnson, Dr. Klitschle, and myself, of course, and Professor Reddy, who started this off. I mean, that's already 2 hours ago, so I almost forgot, but he gave a very nice overview of the situation in India and also where the government should be going to invest in this industry to really kickstart it. And there is initiative taking place, and we hope to see a vibrant seaweed industry really developing now in India over the next 10 years. There is some target set already of 1 million tons in 5 years' time, and that is good. We can work towards that together, and it's great to cooperate in a lot of projects and things to actually really make this happening. So if there is no other comments, no other things to say, then I give my word back to the anchor or Praveen to close this off.
Yeah, thank you,
So much,
Stefan, and for conducting a good discussion and chairing the session. And I thank Dr. Reddy, in fact, he is not here, and Dr. Alan Klitschle, Dr. Mantri, Dr. B. Johnson. So thank you all being present and giving good insight about the technology and the practices in seaweed sector. Yeah, Soni, you can give the concluding remark.
All right. So I think, Pravash, you have done an excellent job. As you know, you have been a beautiful coordinator as well, always, and conducting such a beautiful event, which has been so enriching for all of us. And not only for the people who are in the industry, for us who are learning about it. So thank you so much, all our eminent speakers and participants. I'm sure we all are quite benefited from this. It was an enriching experience. So for now, I would like to thank everyone for joining in and participating. And as we have been telling, if anybody has any query, they can leave on the chat box. So if it's not addressed right now, it definitely will be addressed later. So we are running out of time, and we are going to quickly thank our sponsors, Diamond Partner, SELT, Marine Group, CMFRI and CIFT, media partner EcoPost. And this is, as we all know, organized by Smart AgriPost. I'm Gitanjali R. Soni, your anchor for today. And tomorrow also I will be joining in. I hope that you all are going to be as enthusiastic as you were today. And tomorrow we are going to have another very, very interesting session, seaweed processing, value addition, and product development. So for now, I just wish you all the very best. And whomsoever, whatever suitable time at your end, you just have a great time. Keep shining and smiling. We shall see you all very, very soon. Thank you so much. Have a great day ahead.
Thank you. Thank you.
Thank you very much.
Thank you.
Thank you.
Bye.